But things have changed over the last 15 years. In fact, going a little earlier, going back to 95, where there's now a sort of a new competing candidate where you can explore many-body physics, superfluidity, magnetism, and a variety of other interesting things that we normally find in solid-state environment, rather than the kind of systems I'm going to tell you about, these rarefied atomic gases, trapped atomic gases. So what I'm going to tell you about is so-called paired superfluidity in these resonant atomic gases, alkali gases. There's a number of references I put down. So the primary reference, which is this work with Victor Gurari, a colleague here. Victor Gurari is a long, very long article in the Annals of Physics that's quite comprehensive. So if you want to learn about the subject, both about the S-wave Feshbach resonances and P-wave Feshbach resonances, and using them to create superfluids in degenerate atomic gases, this is the reference to look at. There's also, today I'm also going to talk about other aspects of that work which appeared in collaboration with a couple of my postdocs, Martin Velez and Dan Sheehy. There's a number of other, if you get interested in this subject, there's a number of other references. We did some pretty extensive work with Daniel Sheehy on imbalanced S-wave Feshbach resonances and superfluidity. So there's all this physics about Folder-Ferris states and such that I may mention. But if you want to look in there, that's a reference to look at. And then there's a variety of other works, and of course the field has really exploded. So, but this is a beginning where you can look and follow up on references if you're interested in the subject. So let me then begin with this. So again, these are the outline of what I'm going to talk about. So the course outline of the 2 lectures. I'll be giving 2 lectures, one today, one tomorrow. And they roughly break up into 2 topics: S-wave Feshbach resonance superfluidity and P-wave Feshbach resonance superfluidity. But I can't resist, and it's probably appropriate given probably most of you do not work on cold atoms, to give a little bit of an introduction and put it in perspective before really delving into details. So this part is going to be today, but probably will spill over quite a bit into tomorrow. But that's the plan. I'm going to try to go through some of this, and then leave the P-wave Feshbach resonance with the main topic for tomorrow. Okay, and please interrupt me, as you guys have been very active, particularly first 2 weeks. But some of you have left, and also the rest of you are quite exhausted, and that's understandable. Hopefully we can rekindle that energy and have you interrupt me. I don't need to finish. I just want to give you some flavor of this. There's an enormous amount of information, really, and background. So really, this is just to give you some flavor of what the subject is about. Okay, so let me start out with just sort of ease into the subject by reminding things you probably already have learned, or even if you don't work on the subject, have seen in colloquia, but just give you a little bit of my perspective. So, one way to sort of to summarize the subject of condensed matter physics, and really is to think about what really characterizes this incredibly vast and diverse field, right? And there's really 2 ingredients from my perspective. One is that all the systems in condensed matter physics, almost by definition, consists of macroscopic number of degrees of freedom. That's one. And 2, those macroscopic degrees of freedom have to be interacting. If they're not interacting, it's boring. If there's only few of them, then that's not condensed matter physics. And so, it's really, in some ways, this slide summarizes what we've been trying to do in not just this school, but over the past 15 years of the school. We're trying to cover topics all the way from superconductivity, magnetism, quantum Hall-like physics, but then on alternative years, we'll also talk about soft matter physics, liquid crystals, rubber. And so these are all exciting systems, and what makes them exciting is these 2 features: interactions and macroscopic number of degrees of freedom. So, at least from condensed matter physics' point of view, and somewhat naive, maybe outdated view of atomic physics, atomic physics couldn't be more different than what I just described. There one focuses on sort of much more different physics, looking at individual atomic constituents and looking at spectral individual atoms or molecules. And in fact, one works really hard in order to have precise measurements of this. One works really hard to create really dilute systems so that there's effective interactions between different constituents is minimized. You have, by virtue of just to have a strong enough signal, you have more than one atom typically, although even then you can trap single atoms. But this is sort of the other end of the spectrum of physics, where one wants to look at individual constituents. And so,
sorry.
Yeah.
So in the case of Fermi gases, aren't the more dilute ones more strongly interacting?
If you have cool interaction, right?
Oh, right. Okay. Only if they're charged.
Okay. Yeah. So these are everything's I'm going to talk about today. Although there's a whole subject of ions, and Dave Wineland down the road at NIST received the Nobel Prize for working with trapped ions. But everything I'm going to talk about are neutral ions. So yeah, I mean, of course, I wouldn't be telling you about this if, this paradigm would be too naive. And in fact, when first general atomic gases came on the scene, thanks to the work here by Cornell and Carl Weinman and work at MIT by Wolfgang Ketterle, this was the sort of this kind of a naive viewpoint was kind of the prejudice that, what can they tell us about condensed matter physics? These systems are sort of on the other end of the spectrum in terms of physics that they focus on. And so just to drive that point home, typical systems I'm going to be talking about are incredibly dilute. Their densities are something like 10 to the 12 per centimeter cubed, which is more than 1 million times more dilute than density of air in this room. Mean free paths are like centimeters. So that's incredibly, the atoms are 10,000, maybe 1,000 times more. Distance between atoms is about 1,000 times their hard core size. Okay, so that's really, as from condensed matter point of view, is basically as boring as you can get. But of course, we know in hindsight that with there's really a revolution. It's starting in 1995. There really a revolution is taking place once the rubidium-87 and sodium-23 were condensed and this Bose-Einstein condensation was realized. There was a period of, even at this time, I remember I first arrived to CU in 1995. I remember meeting at Cornell, and he was all excited and showing me his laboratory and telling me about, I guess this was a little bit before, I came to visit before actual condensation was taking place, but was realized. But I remember having a conversation with Eric, and he was all excited, and I was totally dumbfounded. I thought that this was from textbooks, and there's nothing. I didn't realize there was this quest to condense atomic gases. And in fact, I remember going back to going to a Gordon conference, and telling my colleagues, telling members of that conference, attendees of that conference, about projects that's going on in Colorado, and they were also equally dumbfounded of like what could possibly be interesting about a dilute, even if post-condensed atomic gases. So there was a very little appreciation or vision within the condensed matter community about what this field could bring us. And there are notable exceptions like Jason Ho, who really delved right into the field and made and continues to make serious contributions to the subject. But as I hope I will show you, that indeed that initial view and initial kind of dismissiveness, both in the StatMech community and the condensed matter community, was unfounded, a little bit short-sighted. So so there was a period of about, I would say, maybe 5 to 7 years, where now that you realize this object very much like you do with lasers, it's still very dilute, and it's still it's a coherent matter wave that you can think of, and you can stop playing around with it, but really in the realm of weak interactions, when it's still well described by Gross-Pitayevsky equation, and basically you're doing laser physics with atoms, with atomic waves. So early on, people in particular Ketterle's group demonstrated matter interference. This is sort of an analog of two-fringe interference with these dilute atomic gases. Basically, you create this double well potential to trap these atoms, and then releases the well, and these two coherent atomic clouds collide and create this interference pattern. There's, after somewhat of a longish quest to create vortices to really demonstrate that this is not just condensation, but also has other aspects of superfluidity, namely flux quantization or circulation quantization. Beautiful vortex lattices of this really breathtaking quality have been realized by Cornell and then later by other groups. There's, people have studied fluctuations in low-dimensional systems, phase fluctuations. Soon, people then went on to make more interesting condensate systems where there are maybe 2 or 3 component systems. So, for example, here there's a 2-component system, so you trap 2 hyperfine states. You condense 2 hyperfine states, which can transition between those 2 states, so you end up getting something like a spinner 1/2 condensate. And you can watch Rabi oscillations of the spinner condensate now. So it's quite beautiful work. Again, I'm a little biased and a little focused on Eric Cornell's group, but this is the one I remember watching.
What couples to the pseudospin degree of freedom there?
What do you mean? What do you mean?
Like in a normal, in a MRX, it's traditional Rabi oscillations, you hit your spins with some sort of a signal that deorients them. And
Right. What is the analog of the sort of the X component of magnetic field or something like that? It's also the magnetic field. I'm trying to remember now. Yeah, I can't quite remember because this is not a Feshbach resonance system. If there are Feshbach resonance, then you can also use magnetic field to take advantage of Feshbach resonance that I will discuss. But in this system, I don't quite remember. Oh no, so you send an RF pulse. An RF pulse will couple 2 amps of F states, which is what this is. Yeah, so they use an RF pulse, like a pi pulse, or pi over 2 pulse, that will convert half of the population coherently to the other M sub F state, and then it begins to Rabi oscillate. And so you see oscillations in population. Yeah, that's what they do. In Feshbach resonance systems, you can use Feshbach resonance by tuning the magnetic field. Also, more recently, people were able to take actually measure the Boulder spectrum of superfluids. So here's the particle regime, and here's the linear part of the Boulder spectrum, excitation spectrum of a superfluid. Early on, there was also measurements, thermodynamic measurements. So here's a measurement of the energy of the function of temperature, showing that indeed, even for something like 100,000 atoms, you get to thermodynamic limit quite quickly. You see you see a transition. This is not. Yes.
How phonons are measured in core diagram system?
Say it again.
How phonons are measured in core diagram system?
So this is something called Bragg spectroscopy. So you use counter-propagating laser beams that are of different frequency. You can transfer momentum from the laser beam. You absorb a photon at a particular frequency and at a particular momentum, and excite the fluctuation in the excite a phonon or Boulder quasi-particle in the condenser. Something a procedure called Bragg spectroscopy.
Question. So on the lower left panel, the energy spectrum. Is it the energy spectrum?
This is actually, let's see. Yes, I think this is the energy as a function of temperature.
Energy function.
I lost the y-axis, yeah.
So my question is, if you go to the macroscopic limit, would the crossover behavior become the sharp phase transition? that what we would expect?
Well, that's what you would expect, but my point is that even here, I think this may
Sure.
be, you already see a break in the curve, and so if you took a derivative of this to get the heat capacity, you would see that there's something there. So, of course, you will never get to the quality of measurements at 5 order of magnitude measurements of critical exponents and things like that, and that's maybe part of the message that sometimes is missed, and why this subject was maybe at first dismissed as something that could add to it. Whenever in physics you have a new system, that means you have new knobs, you have new experimental tools to interrogate physics. And you shouldn't try to go and replicate, necessarily, things that we already know. Okay? What you should really be doing is thinking about it for its own sake and trying to understand the physics here. So the physics of cold atoms is not, even though it has a lot of overlap with what we already know, and it's not about, for example, doing a better job on critical exponents and trying to compete with helium physics, or doing a better job on something else than we do in, for example, from my perspective, studying disordered systems that we already can do in solid-state environment. It's other directions that the new experimental knobs offer you in this new system. For example, non-equilibrium physics is one big possibility, or Feshbach resonances I will describe. That's really the message and the focus of what I'm going to talk about. So anyway, so this was a brief period, maybe not so brief, maybe 5 to 7 years, where people were really having fun with all kinds of condensates. And in 1999, this story completes itself, where John Marco and Debbie Jin were able to make degenerate Fermi gases. They were able to cool Fermi gases now rather than bosonic isotopes down to below Fermi energy. Okay. So that was a quest that was achieved in 1999, and from that, really the field really took off, both on the sort of a fermionic and the bosonic bench, and basically by now, alkalis, all the alkalis have been, although actually I don't know if, I think every element of alkali has been condensed. I don't know about the fermionic isotopes, and so the primary fermionic, since I'm going to be talking about paired superfluidity, to connect us to superconductivity, I'm going to be focusing on these two atoms, and this is the primarily two atoms that fermionic progress has been made. So lithium-6 and potassium-40. So Debbie Jin, my colleague Debbie Jin in Gila works on potassium-40 as one of the, and this is the first isotope that was, fermionic isotope that was made degenerate. So, okay, and so again, so I return to my question of how do you do condensed matter physics with degenerate atomic gases? And so we need those ingredients. We need the ingredients of many constituents, and we need interactions. So many constituents, well, maybe we're already there. At first condensates were only few tenths of thousands of atoms, but very soon people were able to make millions of atoms. So, potentially, root n, like if number is small compared to n, 1 over root n, and effects are small, so you could start thinking about that you're approaching a thermodynamic limit if you're not too demanding about measuring critical exponents, things like that, but just demonstrating the phenomena, then that's matter physics. But the other ingredient, of course, we need is interactions. And so we need strong interactions. And so there's really two ways one can obtain strong interactions. I'm only going to talk about one of them, but just for completeness, I'll mention this other way, that is optical lattices. Basically what you do is, the idea is that if you can put these fermions or bosons in an optical lattice, then even though the interaction is very weak, you're effectively increasing their density, or another way to think of it is you're suppressing kinetic energy, because now this particle, if you make the wells very deep, the interaction is still the same, but if the two atoms are on the same site, but the hopping matrix element, the kinetic energy, the bandwidth, has now you've reduced from infinity, where you had it in the continuum, down to whatever the hopping matrix element is, and you can tune that and make it as small as you want by simply increasing the intensity of counter-propagating laser beams that create a standing wave that traps these atoms in this periodic potential. Okay, so that's one way, and in fact this is a very successful way, and one of the seminal experiments was done by Marcus Greiner, Manuel Bloch and Company, after suggestion by Intuition Peter Zoller and Company. They were able to realize, Greiner et al. Were able to realize superfluid uninsulated transition where you, by tuning, by starting with a shallow potential, low intensity, where hopping matrix element is large, the kinetic energy is large compared to interactions. So then you sit in a superfluid state, and you see these coherent peaks. You can think of this as a Bose condensation peak, but these guys appear as sort of the Bragg peak echoes of this Bose condensation peak due to the lattice, because you can scatter. Condensate can scatter from the photon and pick up momentum carried by the photon, but provided by these two counter-propagating laser beams. But basically, it's supposed to tell you that we're in a state where phase is a good quantum number. Okay? But then what you can do is you can just tune the intensity of the laser beam, of this trapping laser beam, increase the trapping potential, and therefore decrease the hopping matrix element, and go to a state which, at least within this measurement, is featureless, a number eigen state. Okay, so I don't want to dwell on this. This is more for purposes of sort of just being complete, just to put things in perspective. And with with this realization, the field just exploded. People, if you go to Manuel Bloch's website as one example, or Marcus Greiner, and you'll see that there's just unimaginable richness of both fermionic and bosonic atoms interacting inside periodic optical lattices. And now it's almost, if you read condensed matter papers that propose some exotic state, they're always reference, well, in cold atoms you can do anything, and so they're not sure this model can be realized, no matter how complicated. Of course, in reality, things are very much more challenging, and really this field broke, wide open because of experimental problems. And so it's many of the theoretical proposals for all kinds of exotic states and exotic models are not necessarily realizable. Even this simple, from the point of condensed matter physics, simple model, just the Bose-Hubbard model, took years to realize, and it still poses a number of puzzles. Yeah.
Those higher order peaks, what they have some information in them, like is it some sort of a form factor that tells you about the ground state?
Yeah, I mean it's quite similar to having finite momentum Bragg peaks, and if you scatter, in neutron scatter, X-ray scattering from a lattice potential. So it's just so it's a form factor. They're certainly undetermined. Their relative intensity is determined by the shape of the potential. If it's purely, so it's what the wave functions look like on individual sites. So roughly speaking, this envelope is the Fourier transform of the single site potential, or single site wave function.
That's a real space picture, right? I mean, these images.
This guy?
Yeah.
It's a real space picture, and I don't really want to get into it, otherwise I'll never get to the first half of a lecture. But yeah, so what you're really seeing in real space, in far field, is actually a Fourier transform. You're actually seeing a momentum distribution function.
Right.
And the reason for that is, sort of Fourier optics, essentially.
So do those other little peaks, do they move, or are they stationary? Do they stay there? I mean,
Well, this is a static image.
Are they spreading out, those other little?
No, they're not moving.
Okay.
They're just this distance in real space is completely determined by the reciprocal lattice momentum. reciprocal lattice vector defining that periodic potential. Actually, let me think about that. Then you may be right. So let me, yeah, so the condition is H bar K yeah, so no, you're actually right. So thank you for that comment. So the condition is what you see in real space is the position of the peak. What you see in real space is the position that the atom would travel to, a set of atoms would travel to with momentum k. So this is momentum divided by mass, that's velocity times time. So if you wait time t, a set of atoms that had momentum k will travel this distance. And so you'll see them if you take a snapshot, if you do this time of flight image after time t. That's how you can understand, in fact, why you have such a sharp, for example, this peak, the most condensation peak. It's a Fourier transform. It's a Fourier transform at this k, where you're seeing it is at this position. So if all the atoms at single momentum, namely low momentum, then they won't move anywhere, right? But the ones that have scattered from a photon from the optical lattice, they will move with an additional momentum. But you take a snapshot of it, so it's some fixed time. Yeah, thanks. Okay.
I'm sorry, just to verify. This is K-space, right?
You're taking...
one thing is how you measure it. And actually...
right.
Yeah, I don't...
This is an absorption image. This is an absorption image through the cloud that's been expanding after you shut off the optical periodic potential. And you just you measure the resonant light through the cloud, and you see peaks, okay, absorption peaks. And so you see this image in real space. But what it tells you about, if you wait long enough, so you're in a time of flight limit, what you really see is a Fourier transform, where the relation position is actually proportional to k times time.
Okay, perfect. Yeah.
Okay.
Yeah.
What is the third one? You have two superfluid.
You go back. That's the beauty of it. You can just tune, just like on the computer, you can tune it back and forth. You can do it suddenly, or you can do it adiabatically. It's kind of an incredible thing.
These three images are simply obtained at different time of
No, they're obtained from my PowerPoint by putting them together. I don't know. I've forgotten actually. You can go back. These are destructive images, and so destructive measurement, and so this time of flight. So this is not like you have to repeat the experiment to actually get there, to get it to go back. So that's a little caveat. Okay, so that's one way to get strong interactions is these optical lattices. The other is Feshbach resonances. So I'm going to first give you kind of an overview, colloquium level overview of Feshbach resonance, just to get that out of the way. But then we'll get into the get to look under the hood once we get into the more of the mathematics. So the other way is Feshbach resonances. They're effectively, and there's a lot that goes on in that word, effectively, a way of tuning interactions, and you can tune both the strength and sign of the interactions. And again, there's some provisos with when I say this. This really should be in quotes, and you can do it suddenly or adiabatically. So it's really an amazing knob that certainly doesn't exist in simple ways or at all in solid-state systems. And those are the kind of things that attract us to think about, for example, superfluidity or other phenomena in cold atoms. So how do you understand this? Well, let me give you kind of, again, colloquium level view. So typically, so these atoms, you have these alkali atoms, let's say, they interact, under generic conditions, they interact by some van der Waals potential. And its range is maybe 50 Bohr or something like this, and it's fixed, and it's some number. And so there's just a bunch of hard particles, quantum mechanical bosons or fermions, and they interact by this potential. So typically, if we had to describe what that is, we would describe it by some 4 boson or 2 boson. I always have a problem with this language, but we describe it by some psi dagger, psi dagger, psi psi, with some scattering length. front. Okay, and that's the background scattering length, and that's the interaction. And because density of particles, yeah.
Just to check the language. Interaction or scattering line? You know, they're...
Well, that's the subject of, that's why I said I'll give you a colloquial view, okay? We'll see that, and as you know, scattering length is not interaction, that's why the simple picture will not be true, but it is interaction when scattering length is small. When the scattering length is small, you can think of it as, when interaction is weak, scattering length is small, you can think in Born approximation as a good approximation, and then interaction is just a, scattering length, or scattering amplitude is just a Fourier transform of the interaction. And this scattering amplitude is proportional to the scattering length. Okay? So that's kind of the generic picture, and that's why we model it by some local short-range interaction. Okay, like a delta function interaction, because on the scale of this density, this guy is, this guy is tiny compared to interparticle spacing. Okay, and so you can see that here already. This is density, and so if I compare this to the kinetic energy, and if I restore units here, there's 4 pi h bar over m. So this guy times this density in 3 dimensions is energy. And so if I compare this to the kinetic energy, which goes as density to 2/3 power in 3 dimensions, then you can see that this guy, when this is small, then this thing is subdominant, so I can approximate by simply a Born approximation of interactions. Anyway, so this is the nature of this typical description. You have just some delta function interaction. But in reality, these are not featureless atoms. They're labeled by their hyperfine states. Okay, so even for two fixed hyperfine states, let's say 9/2 for the potassium, 9/2 and 9/2, there's a huge number of m sub f levels that describe these atoms. And so when they scatter, so there's a huge number of channels that these atoms can scatter in. So then when they're in your trap, they're in particular m sub f states. But then when they scatter, there are nearby other channels or other states that when the atoms scatter, that they can scatter into. And so when those channels are, so typically the channel that the atoms are in your trap, the ones that have, for which the potential interaction goes to 0 at far separation, then that's called the open channel in the jargon of the field. And the other channels are called the closed channels. Okay? And they're closed because when the atoms are far apart in the presence of a magnetic field, this is an excited state. So the atoms live in this state. But when they come close together, you can have, if you tune things properly, you can bring some of these closed channels nearby, near the 0 energy continuum of the open channel. And so when these two atoms are scattering, they can scatter through a bound state, a quasi-bound state of some other quasi-potential in other quantum states of those two atoms. Okay, so you can think of this a little bit like there's a continuum of states. That's the open channel, and those continuous states in this channel that there may not be even a bound state. Think of this as even flat, the blue curve. It's too shallow to create a bound state. But then there's a resonant state level, much like when we discussed Kondo or Anderson model, and this level can be tuned through this continuum. And it affects resonant properties, scattering properties of the atoms in this open channel.
Sorry, maybe this is just a bookkeeping question, but you said that the interaction going to not zero at infinity corresponds to it being some sort of an excited state. So
right.
So I would have expected that to be part of like the single particle Hamiltonian of this system? So we're putting it into the interactions here?
Yeah, so the way this is drawn, I'm putting in this interaction potential. So this is all done in the presence of magnetic field, and these different channels have a different magnetic moment, so they have a different Zeeman energy. And so when the particles are far apart, they have different Zeeman energy. They're in different different total magnetic, different channels correspond to different magnetic moment, and therefore different Zeeman energies. And so this state is not really active unless it only begins to be important when the particles come close together and they interact, and so then these channels begin to be mixed.
Okay, so you don't include it in the single particle Hamiltonian. From the perspective of the single particle Hamiltonian, there's just the one channel, and it's only in the interactions that you get virtual processes that populate these other ones? I'm just a little bit confused because this is different than how we normally include the same amount of energies in Hamiltonians and condensed matter.
I mean, so there's different bases I can use. So simplest base, the problem is of describing this, it's always like when I was first learning about this, and you don't really learn it, which means I've never really learned it, unless you talk to John Bowen, my colleague in Gila, and really do like multi-channel calculations and really produce these adiabatic potentials. But really, when you imagine doing it, and okay, so the problem in the description is neither far apart nor close together. There's no simple, there are no single bases which is good throughout. Okay, so but you can choose a basis and simply project your microscopic Hamiltonian onto that basis, and the basis would be, let's say, product of M sub F hyperfine states for this atom and this atom. And then you simply write down a Hamiltonian in that basis. And you project the interactions, the whole thing, onto that basis. And then presence of magnetic field, for example, that's already a bad basis, because the magnetic field couples much strongly to the electronic part of the magnetic moment corresponding to contribution from the electronic spin than from the nuclear spin. And so even that basis, even when the atoms are far apart in the present magnetic field, is not an ideal description. But a kind of a qualitative way to think of it, one qualitative way, one limit to think of it where the interaction dominates is, you can think of this as this trapping guy as a spin singlet channel, and sometimes that's what's used in the jargon of the trade, and this is spin triplet channel. So look what I've done here. So this notation is a little bit, so I use red and blue atom to say these are two different distinct fermions, distinguishable fermions. So two different isospin states, labeled, let's say, by hyperfine states. But on the other hand, I draw these labels, spin up, but here I do spin up and spin down. So what these errors represent, I guess in qualitative sense, because these are not really eigenstates of, spin is not a good quantum number, electronic spin is not a good quantum number, but this is supposed to represent spin, electronic spin. So, so here in this channel, roughly speaking, electronic spin is approximately a singlet of these two atoms, and here it's a triplet. And because from this perspective, when you have hyperfine interaction, that couples this triplet channel to the singlet channel, because when these two guys come together in this electron triplet channel, they scatter. By virtue of hyperfine interaction, you can flip an electronic spin and a nuclear spin and go to the singlet channel. And the singlet channel, just like an H2 molecule, is much more strongly bound, so it's deeper, and so it allows for a bound state. Yeah, Andre?
Should we view it as two fermions really due to hyperfine interaction going to singlet channel, form bound state, virtual bound state, and then go back and this effectively produce interaction between fermions? In other words, should we view this as a virtual bound state?
Of course. Yeah, of course. Absolutely. And so that's in fact what, I'm walking through this. So the way I think of this is, rather than having this featureless four Fermi interaction or four boson interaction, this kind of an interaction, contact interaction, you really should think of it as a two atoms scattering through some kind of a resonance, some kind of a quasi-bound state. If there was no hyperfine interaction, it would be a true bound state. But because of the hyperfine interaction, the singlet and triplet channels can mix, mixed by a hyperfine interaction. So the language depends a lot on what basis I'm using. That's why it's a little confusing. I've been working this long enough, but it's still confusing to me because I'm not a numerics person who goes and actually does these calculations, but I know how they're done.
Yeah.
Okay.
Yeah.
Yeah.
So the spins here are, you mean electron spin?
Well, electron spin is not a good quantum number. Okay? But neither is the hyperfine states. So if a magnetic field was 0, okay, then I would just label them, when the atoms are far apart, I just label them by hyperfine states, M sub F states, which is the combination of nuclear spin and electronic spin. Okay, so those are the good quantum numbers. That's in fact what I, let's see if I did it here. Yeah, so for example, if you take potassium-40 has nuclear spin 4 and spin 1/2, L equals to 0 and N equals to 4. So then you form 4 plus a half and 4 minus a half F states, hyperfine states. And then they have a whole ladder of M sub F states. Okay, and so that's how you label, if there was no magnetic field, that's how you would label, these two states, these states of these two atoms. But when they interact, that's not, and also in the presence of magnetic field, that's not a basis that, those are not the eigenstates of the system. Okay, so now you get this really cool, once you have this intermediate state, by tuning with a magnetic field, the relative energy of these asymptotic states, you're tuning this resonance, you label by omega 0, you're tuning it from this 0 particle continuum, 2 particle continuum, and as a result you have a resonance scattering between these two atoms through this quasi-bound state, and so your scattering length, you can vary your scattering length. So you start out with some background positive scattering length, and then when you get close to the resonance, just by second order perturbation theory, this is positive, you end up getting an effective attractive interaction because of, if you get close enough to overcome this small positive background scattering length, which is fixed. And so now you get to, as you tune the magnetic field or you tune the Zeeman energy closer to the Feshbach resonance, you make the scattering length negative. And if you go to the resonance, scattering length actually diverges. And in this regime, once it's large, you can't think of it as interaction anymore. It's really just the T matrix. It's one of the. It's a property of the T matrix with the scattering like this, and it enters into the scattering cross section, thing like that. But you shouldn't think of it as interaction. The interaction in these systems is always attractive. Okay. Well, okay. So, it depends on this background scattering, I guess I should say. But the fact that you change the sign of the scattering doesn't mean you change the sign of interaction necessarily. They're only proportional to each other in this kind of a simplest weak interaction Born approximation limit.
So this interaction is really, this resonance is a resonance between a triplet and a singlet state?
Approximately. In this, it's a resonance between, it's a resonance scattering between these two atoms through this intermediate spin singlet state.
Right, there's a resonance between triplet and singlet.
Yeah. But it's not singlet and triplet in the hyperfine basis. It's not a singlet and triplet in the hyperfine basis.
Right, but if you take hyperfine interactions artificially small, then it will be.
Then it's true. Then, yeah, so the way you can think of it, suppose I take hyperfine interaction as the perturbation, which is not how we typically label these states when they're far away. If it's a perturbation to interaction, if you take hyperfine interaction to be weak compared to the interaction between atoms when they're close together, which determines the shape of these potential at small separation, then you can think of this as an electron singlet, an electron triplet, and a hyperfine interaction mixes them because the spin can flip by also flipping a nuclear component of the spin. by flipping nucleus. Okay. Okay. So by tuning the magnetic field, I can bring this level down below and make it a true bound state. And at that point, whenever you have a bound state formation, scattering length changes sign. And so now I can go to a large positive scattering length. I can tune it beyond that. But you have to appreciate, just because the scattering lengths change sign, sometimes we refer to this side as the repulsive interaction. It's not really repulsive. It's really still attractive. That's why you have a bound state. But if you ignore the bound state, for the scattering states, it looks like it's repulsion. The wave functions are shifted away. But you now have a bound state. So strictly speaking, you need to worry about that bound state if you're close to the resonance. So you can't just call it a repulsive interaction.
So far this looks very similar to me, the BCS-BC crossover. Should I think of it this way?
Well, I'm talking about two atoms, so there's no BCS-BC crossover. All I'm doing is being very elaborate because this is a spool. This is typically, I just showed this in maybe 30 seconds. This is just a summary of the resonance scattering physics for two atoms. This is going to be the building block for BCS-BC crossover.
Okay, that's my question.
Absolutely. That's what I'm getting to. So I'm distinguishing Feshbach resonances and scattering, Feshbach resonance scattering versus Feshbach resonance superfluidity. And the distinction is two atoms versus Avogadro number of atoms, or at least a million number of atoms. So so if you actually go and calculate, and I will do that, hopefully I'll get to that. If you actually go and calculate the scattering amplitude of these two atoms through this resonant process, and then you look at the poles of that scattering amplitude, and look at the real part of that pole, you can plot the value of that real part of that pole. That's the energy of your state. That tells you about the states. That's another way to solve Schrödinger equation. Find the scattering amplitude and look at its poles. So if you look, and so let's plot this real part of the energy as a function of 1 over the scattering length, minus 1 over the scattering length. So what you see is, when the scattering length is positive, which means you're on this side, it's just a convention. We put minus 1 over 8. So that means when you're in this regime, then you're over here. You're on the positive axis. And when you went and formed the bound state, you're on the left side of the axis. So what you see is you get a bound if you go to this state. Sorry. If you've detuned such that this resonance is below the scattering continuum, zero energy continuum, then you get a true bound state. Here it is. Zero width bound state. Okay? On the other hand, if you're on the attractive side where you detune, this is just a virtual state, that just creates some attraction, but that attraction doesn't create true bound state of these two atoms because the two atoms scatter into this, they bounce around for a while, and then they decay back out. And so you don't have a true bound state, but you have a resonance, and this has a width. So the message is on the left side, on the repulsive side, when you form the bound state, there's a true zero, physical bound state, and on the attractive side, we'll call this later BCS-BC. All this is the resonance, finite lifetime resonance. Okay.
So there's a critical scale there.
That's right.
What does that represent?
It depends on the width of the resonance. So this is actually quite important, and I'll get into that. This is called the effective range. This parameter are not called the effective range. So it's not just, things are not just determined by the scattering length, there's also another length scale in the problem called the effective range. In fact, most of the experiments are done in this little circle where you don't see this resonance. So Feshbach resonances for most experiments don't have a resonance in them, as oxymoronic as that sounds. And I hope to explain that. Okay? In order to see a resonance, you have to get far enough from the Feshbach, from the true resonance to see this resonance state. You have to get to momenta that are large compared to 1 over this R naught. But if your KF, if your density of atoms, if your number of atoms in the trap is small enough, such that your KF is too small, then you never get to the scale. You're sitting somewhere in a circle. So typically you'll see in the subject, discussion of the subject, people just draw this. They draw a little circle around here, they don't show this resonance. So the way you can think of it, if this picture is confusing, there's an effective model you can write down. It's very simple. You simply think of a binding potential with a big barrier. So so now let's introduce a couple, so let's think of the barrier infinite first. So now there's a bound state and there's a continuum outside. Now we just simply write down a matrix, 2 by 2 matrix that couples the single bound state to the continuum outside. Okay, so not surprised, and then imagine, so tuning this omega 0, which is the microscopic way you're doing this, through Zeeman energy and through these channels, you can model it by simply tuning the bottom of this well. If the well is higher than a certain value, such that this bound state is above the 0 of energy, then it can leak out, and so it has a finite lifetime. And that's this resonance. And it just virtually gives you attraction. On the other hand, if this resonance is below 0, then you have a true bound state, at least forever. That's a sort of a simplified, macroscopically and inaccurate picture, but effectively it's the correct way you should think about it. Now, if I get rid of the barrier, if you want to understand, Sam asked me about this. If I get rid of the barrier, so imagine getting rid of the barrier. If I get rid of the barrier, or make it small enough, then the lifetime of this thing is so short that I never see a resonance. I basically either, for any positive energy, I won't see a resonance state, because it basically leaks out faster than its energy. So this has some energy and it has some lifetime, a tunneling rate. If that tunneling rate is small, is larger than the energy itself, which will happen if I don't have a barrier, then I don't ever see this part. But I still have a resonance in the sense of when I approach 0 energy of scattering with these particles, I will start forming, I know, my scattering amplitude knows about vicinity of this bound state that's about to form. Okay? And here I should point out, this is some of the earliest measurements from Debbie Jin's lab, done in the thesis of Sidney Regal, who's a faculty now here, of the scattering length and showing how you actually get this behavior that behaves sort of like this.
How is that measured?
So there's a variety of ways to measure. In one way, the simplest way is to simply 3-body decay. You simply watch, as you approach the resonance, you notice your atoms begin to disappear. And you ask, what's the rate at which they disappear? Well, how long do they live? And so the 3-body turns on with this. There's a simple theory of 3-body decay, and it's proportional to, it depends on A squared. And so from that you can back it up. The other way is you can measure it spectroscopically, and that's how this was done. You simply look at the Hartree shifts. You simply look at your spectrum of your potassium-40 atoms, and you ask you look at the hyperfine levels, and you ask about how are that spectrum changed by this. So you have a Hartree shift, which is the density times 4 pi h bar squared A divided by M. So this is the Hartree shift. Okay? And so they simply see how their levels move around for fixed density as a function of A. And from that they can map out A. Okay? And there's a number of other ways you can measure, you can extract scattering. Okay? And here's a measurement they extracted also of the bound state. And the bound state you will not be surprised, it just goes as h bar squared over 2m a squared. That's that parabola. Okay, so Feshbach resonance, so just to, we're about, an hour into it. So think of it as a comic relief, or think about it as my way to emphasize how important Feshbach resonances are. There was actually a song written about Feshbach resonances that I want to play for you. Well, let me give you some background. So, sometime back, I guess in 2005, Dan Sheehy and I wrote a PRL about, doesn't really matter what it's about, but it's using Feshbach resonances well, here's the title of it, Quantum Decoupling Transition in One-Dimensional Superfluid. So we consider 1D version of this fermionic superfluid. There's a, rather than BC-SBC crossover, there's some interesting quantum phase transition takes place there that we explored. We wrote a paper about it and forgotten about it. But then at some point, maybe, I don't know, like 5 years later, I get a link, I get an email from this guy who I had no idea who he was, Jonathan Mann, who said, hey, you might enjoy a song I wrote. So I don't know why or what the background was, but he decided to, there's a songwriter in California, and he decided to, out of thousands and hundreds of thousands of papers that are written each year, he looked up our paper and decided to write a song based on its abstract. So it's totally, he just basically verbatim sings the abstract of our song, of our paper. And I looked a little bit more into it. There was, I guess, online interview of They Might Be Giants, this band. They came up, well, I didn't know. I had to consult my daughter, teenage daughter, to explain to me who Might Be Giants are. So they just came out with a new album called Here Comes Science. So they were being interviewed, and you know, so they're talking about what, you know, importance of science in the modern world, blah blah blah, education. And at some point, out of the blue, the interviewer says, "Well, you guys think you're so hot. Well, how about I give you some really obscure expression and see if you can make a song out of it right on the spot." And so then he says, "Okay, quantum decoupling transition in one-dimensional superfluid." So then they try to sing it in a variety of genres. First, like decoupling, they thought, oh, it's a breakup, so it must be really sad. So they sing like it's sad. And then they said, okay, let's sing it in a different genre, quantum. Okay, and then it's like all this quantum genre. And so they do that for a while. So apparently Jonathan Mann, who actually went on the mission of writing a song a day, he decided, like, maybe a way to make progress is not to write one good song, like after 10 years, but try lots of little ones every day. So I'm going to write one song every day. And this is like song 347 or something like that. And so he was listening to this webcast, and so he said, oh, I'm going to upstage these guys. I'm going to write a whole abstract. I'm going to sing a whole abstract. I'm going to make a song based on the whole abstract. So he looked up this. But anyway, so I apologize if, oops, if you can't, you won't be able to get the tune out of your head after this.
The audio plugged in?
Can you hear it?
Yeah.
I don't understand why it's not playing the video. Huh? No, it's not. No, but you gotta see this guy. That's part of the fun. So sad. Do you hear what he says? Okay, you get the point. But I'm really sad that you were not able to
Email us.
Well, you can see that just all you do is say quantum decoupling transition. That's the first hit that comes up. Okay, so let's go back to physics. Okay, it's kind of fun. Of course, I send them all these other abstracts. They just ignored me. But the other sad part of the story is that in like a couple of weeks, this link had more hits than I could ever hope to have. Reference to my paper citation. And all of us together. But anyway. Okay, so now I'm going to get into a little bit more detail. hopefully to answer some of the more technical questions, though given the shortness of the time, not really everything. So let me now talk about S-wave Feshbach resonance superfluidity. So before I do that, let me start with do a little bit of scattering theory, just to at least define terms, and then I'm going to talk a little bit about scattering theory, in particular two-channel model for scattering theory. And then I will talk about how to use this two-channel model to describe superfluidity. And so the message is really, before you do superfluidity, you have to understand scattering theory first of the system. Okay, so you need to understand resonance scattering theory. And this model, where you think of it as the way you model this is in terms of a closed channel boson, this bound state of two fermions, and the continuum of fermions in the open channel is so-called two-channel model, because there are two channels involved. In reality, of course, there's a huge number of channels, 36 channels or something, well, it depends on the atom, that we're ignoring because they're far detuned. Okay, so this is the dominant thing. So then I'm going to talk about two-channel resonant superfluidity, and that's appropriate for narrow resonance. The resonance is narrow, that's a good description. Well, in fact, it's universal description, it's general description, but as I will show, when the resonance becomes broad, meaning this molecule doesn't live for a very long time, or the barrier between the bound state and the continuum of states is small, then this two-channel model becomes a single-channel model, because you can effectively integrate out this boson, and you get a full Fermi interaction that you're more familiar with. Then if I have time, I'll describe the Largian theory, Largian SBN theory of this, and then talk about universality. Okay, so just to define terms, I can't, this is a whole course, this is a fraction of a course. So, the way we describe scattering of atoms is using scattering theory, using Green's functions. So in fact, you can think of this as a way to solve, a complementary way to solve Schrödinger equation. You have a particle in the potential, and at some energy E. So then you write that the way to formally solve this is simply write psi as some psi 0 when they're far separated, plus 1 over times some plus some propagated times v times psi. That's a formal solution of this differential equation. So if you think about it, this is just the homogeneous solution, and this is the bring this to the right hand side. Bring this to the left-hand side, bring this to the right-hand side. Think of it as the source term, and this is the Green's function for the Schrödinger equation in energy space. Okay? And so this is the source term, and so therefore this is just the source times the Green's function. That's all. Okay, so standard stuff. But then, so this is V times the interacting psi. So this is useless, in a sense, because I don't know what psi is. But I could iterate this equation. I can put for this psi to lowest order, I could put psi 0. And that's Born approximation. Then I can put then instead of for the second order level, I can put psi 0 plus this piece. And so on, I can iterate it, and so I can, in the end, of course, I can re-express the whole right-hand side in terms of psi 0 times some unknown so-called T matrix. So a T matrix is what relates this psi 0 to this psi. And to lowest order, of course, it's exactly the potential. T is nothing more than V, right? If it's weak. And so you can do this. So T matrix, if you do this iteration, T matrix is V plus V times the Green's function times V and so on. It's a geometric series. And here it is diagrammatically, expressed diagrammatically. So if you do it for, let's say, plane waves, here's the formal expression for it. You have this 1 over E minus H naught is just K squared minus K prime squared. And these formal inner products are really just summations over K once you go to coordinate representation or momentum representation. Here's the plane wave state when the atoms are far from the potential, and then it's being perturbed by this. And so if you then do this integral using just residues, you get the T matrix times the spherical wave. And so this T matrix is proportional to the scattering length and related to the scattering amplitude. So the scattering amplitude is simply this factor, just by definition. F, so this is the scattering amplitude to scatter from momentum state K to K prime. And because it really only depends on the angle between K and K prime, you can have this representation in terms of the Legendre polynomials. Where the coefficients, so this is, if the scattering potential is rotationally invariant, you can write this like that, where these guys are the different angular momentum channel scattering amplitudes, F sub L's. So then they only depend on the magnitude and the scattering channel. So when I say S wave channel, I just mean I'm focusing on this F sub 0, or F sub S.
Before you go further, so K prime and K are constrained to be what? On the modulus of K should be fixed.
It's fixed by the energy. Well, it's fixed by the energy by this pole. It's not, this is fixed, K squared is fixed. That's the energy of the incoming particle. And then K prime will automatically gets fixed to K squared when you do the,
Because the real part of the integral is 0 and the imaginary part is there.
Exactly, exactly.
So, sorry, I don't understand actually. So you're integrating only over
K prime.
You're integrating over K prime, but then K prime appears on the right hand side.
Right, okay, so that's related to his question. K prime here has been fixed to have the magnitude of, it still depends on the angle. So,
yeah, when you integrate here over K prime, real part goes away and imaginary part puts modulus of K prime.
right, so the modulus of this K prime equals to the modulus of K.
Okay, so there's...
But there's still an angular degree of freedom. It still depends on the angle. Okay, and so in terms of this scattering amplitude, F sub L, you have the scattering matrix is defined as it's e to the I2 times the phase, scattering phase shift, and it's related to F in this way. So from this immediately you can actually show that the scattering amplitude, without doing any calculations, you can show that the scattering amplitude has to have a certain form. And in particular has to have a form F sub K has to be some function Fk minus Ik. Okay, so it must have that form by Unitarian. And the way you do that is take an absolute value of this guy squared. You get a 1. Okay, and then therefore take an absolute value of this squared equals to 1. Then you can show that the imaginary part of the inverse of the scattering amplitude is minus Ik. Yeah?
The function you defined under scattering amplitude is a function of 2 variables, K prime and K.
Right.
The function you put in the blackboard is a function of 1 variable. So there should be a connection between the two functions.
Right. Well, the magnitude, there are K and K prime are on shell, so the magnitude of, so it just depends on this function just depends on the magnitude of K.
So it's F
And the magnitude of K, and magnitude of K prime,
So that should be F sub L in the back. Right.
oh yeah, it's F sub L, sorry, thank you. Yeah, that's why I have this label up. Thank you.
And sorry, just in the top line, psi equals the right-hand side of that equation. There's an implicit integral over the direction of K prime there.
Here?
On the right. On the right. Right. Psi should be a function of r, the position.
Right, right.
So
There's an implicit integral over the angle still.
Okay.
But then I break it up into different angle momentum channels. And focus, for example, on the whatever channel.
Sorry, what is capital F?
Capital F, I don't know. So let me just maybe do this calculation. Hopefully I don't screw it up. So if you take SL, so this is our known function. But if I solve this, if I actually try to find T matrix, I will compute this function. Scattering length will be in here. Okay? But, so let's just look at this. So this is e to the I2 delta L equals to 1 over 2 IK F plus 1, FL plus 1. So let me take a square of this, so you get 1. And when I take a square of this, sorry, I don't know why I wrote 1 over. When I take a square of this, 2IK F plus 1 squared, so I get 1. Then I get plus 4K k squared FL star FL. And the cross term is 2ik FL minus FL star. Okay, so ones cancel. And so now let me divide by this quantity. So if I divide by that quantity, then I get this becomes FL star inverse minus FL inverse. So what is this? This is an imaginary part of FL inverses. And that equals to, if I bring this to the other side, that's equals to IK. So therefore, the inverse FL has to have an imaginary part, and by unit, so this is unitarity, is required to be minus IK. Yeah?
Why is delta defined there, and why is the phase shift?
That's just a definition of,
But,
if you work through, I don't want to do it here, but if you go back to your quantum mechanics, quantum 2 or something like that, that's how the phase shift is defined. That's one way to define the phase shift. Okay, I didn't mean to get stuck here. So this is the summarize what I just said. Now for S wave, this function f is actually just a function of k squared. Okay, it's an analytic function of k squared, so that you can expand it. So it has a constant term, has a just Taylor series expanded around low energies. So there's a constant part, it has a k squared part, and so on. So, and then just for your reference, if it's you can show by just analyzing Schrödinger equation that this function, what I call FL of k, is actually k to the minus 2l times FL, different function FL k squared. So this guy is Taylor expandable in k squared, but it's multiplied for the Lth channel, it's multiplied by k to the minus 2l. Okay. So anyway, I don't want to get into too much into it, but this is the form at low energies. The point is, at low energies, no matter what your model is, the scattering is described by something like this. This is dictated by unitarity, and this is dictated by just general properties of the Schrödinger equation, that it's going to be a constant plus k squared and so on. So there are two parameters. This guy we're going to call inverse scattering length, as you will see. Well, why is that? Because if I go to zero energy, k0, this is Fs is equals to minus a, and that's related to that's how it's defined. That's how the scattering length is defined. Because if I square this, multiply by 4 pi, that's what I get. I get the scattering cross section. But then there's another parameter here. At very low energies, this parameter may not be important. But if I want to understand the resonance, this parameter is very important. It's called the effective range. It also has units of length. As you can see, everything here is 1 over length. So this has to have units of length. And it turns out for narrow Feshbach resonance, the ones with a big barrier and these two channels, that length scale is negative. You can show it's always negative. So that's important. If it wasn't negative, then you wouldn't have a resonance. Okay, you would miss the resonance. So again, so that's going to analyze this a little bit. Suppose I'm really low energies. So I ignore this guy. So then I look at the poles of this thing. This is what I was telling you in sort of the colloquial style of review of Feshbach resonance. I just look at the pole. The pole appears at IA inverse. Right, at IA inverse, and then you can calculate the energy of that pole. It's minus h bar squared over 2m RA squared. Okay, this is something I forgot to say. So when I reviewed scattering theory, that was for particle scattering against the potential, but of course for two particles we can go to a relative coordinate system, and then all you have is the same exact thing as on the previous slide, as scattering a single particle from a potential, but with a reduced mass, which is half of the particle's identity mass. So then I get this bound state, and that's exactly what I drew at some point. This is exactly what I wrote down. Okay? And so at these low energies, really what you're capturing is, there's a bound state here, and there's nothing on this side. There's no resonant state. There's only a bound state. And so this is that's what you see. On the other hand, if you want to look at intermediate energies, which we'll need to do if we want to understand narrow Feshbach resonances, I really have to take this into account as well. So I imagine I can go to energies high enough that this term is bigger than that term. So imagine K is determined by Kf, for example. Okay, once I have finite density. Then I really need to include this term. Then I don't want to go through this because it's, it makes my head spin. You have to really do it carefully with watching exactly what sheet you're on as you're looking at the poles of this scattering amplitude. But it's standard. It's just a quadratic equation, and you look at where's the pole, what is K, as a function of the inverse scattering length. So you vary A, and you ask, how does the pole move? Here's the expression, just all I did is solve quadratic equation, and that describes scattering with this large barrier. So then the lifetime is small. Sorry, lifetime is long. And so you have to look at exactly, not every value of this pole, value of K that solves this quadratic equation, actually corresponds to a true state. Physical solution of the Schrödinger equation. So after you do this, you realize that when you have a bound state, then you have a quadratically varying energy. So you have a state here which corresponds to the bound state, which is the extension of this guy to larger energies. And you can see here, well, okay, so it goes quadratically with 1 over A, but then it comes asymptotes to, when you get to energies that this is larger than that, it grows linearly. It begins to grow linearly with 1 over A. And you can just understand that by looking at this quadratic equation. But then on the other side, rather than having this nothing on the other side, which represents this scattering without a barrier, you actually have, for a while, you have no state, no physical state. So this dotted line, dotted curve between here and here does not really correspond to a physical solution of a Schrödinger equation. It is a part of the, it is a pole in the scattering amplitude, but it doesn't correspond to a physical solution. So it's called in the jargon, if you look in Landau literature, it's called the virtual bound state. But when you 1 over A exceeds 1 over R naught, minus 1 over R naught, then you get a resonance. You have so that means this E will have a real part which is positive and an imaginary part which is negative. That's how you know it's physical. The reason these guys aren't physical, it sounds a little mysterious. We're simply asking what is the value, the real part and imaginary part of this pole. If the imaginary part is positive, then you dismiss it. It's not a physical solution to the Schrödinger equation.
Is this a causality thing? Like, where is that? You don't have.
Yeah. Let me not get into that.
Okay.
But,
Well, it's coming from the formula for psi.
yeah. So yeah, exactly. That's why I wrote this. So you can't. Okay, but fundamentally, you want to have states that decay. Yeah. So you can say causality. This, by the way, for example, this already happened here. I didn't mention it. So look, you might say, you should be all challenging me and saying, wait a minute, you got K pole in the simplest case. K pole equals to I A inverse. So I go and put that into K squared over 2M, and I get this formula. And then I say, oh, here it's a bound state. But here I don't draw anything. Why isn't Sam all over me saying, why is not a bound state on the other side? Well, again, it comes from this formula. So here's the wave function. I have to say, okay, forget this part. I put the IK pole R into here. So let me write that down. Psi is e to the IK pole R, but that's e to the I, and the pole is at IA inverse. So it's IA inverse, it's minus R over A. So when A is positive, this is a normalizable state, and that is the bound state. That's how the bound state behaves. But when A is negative on the other side, I don't think of it as a bound state. It still affects the sort of analytical properties of my scattering amplitude, but it's not. It doesn't correspond to a bound state. So I draw this as a dotted line. But that dotted line actually has a complicated. There's two roots here, and there's actually two roots everywhere, but then here they meet, and they finally become a resonance. Okay? So anyway, so how do we describe this? So a simple model that captures all this interesting physics, particularly this form of the scattering amplitude. So notice I just wrote it completely on general principles. Ik comes from unitarity, and this guy comes from analytical properties of this function f. That is Taylor expandable around zero energy. But now I want a model that produces that. Once I come up with a simple field theory model that produces that scattering, then I'm just going to study that model for finite number of particles at a finite density. And then I'm going to hope that's a good description of Feshbach resonant superfluidity. Okay? So what is the model? Well, again, here's my scattering. Here's the cartoon for it. I'm going to introduce a field phi, bosonic field phi, as a point boson described in this molecule, in this closed channel. And then there's going to be psi up and psi down described in these red and blue atoms scattering in two hyperfine M sub f states. Okay? So here's the model, and that's what we call two-channel model. So there's a kinetic energy for the two fermions here. There's a kinetic energy for the boson. Its mass is twice as the mass of this of the fermions. There's a parameter that captures the relative energy of this guy relative to the zero continuum. I call it epsilon zero rather than omega zero because omega zero is a physical observable that's actually related to the scattering length. This guy is just some parameter in the Hamiltonian. I don't a priori know how it's related to the omega zero. But what you will see is there's going to be a renormalization of the scattering properties, and this epsilon zero is just this physical omega zero is just a shifted version of epsilon zero. It's much like when you do 5-4 theory, let's say studying TC of an Ising model. There's a shift in the transition temperature. There's a T, that's a T sub 0, and then there's a T to true T, and there's an ultraviolet shift of the transition temperature from the mean field value, bare value, to the true value. So that's going to be the relation looking ahead between omega 0, which is physical, and this guy is just a parameter in the Hamiltonian. And then I have so this is atoms, this is molecules, and then there's an interconversion term. A molecule can decay into two atoms. That's it, into a pair of atoms. And so this guy G is proportional to the hyperfine interaction.
Could I have thought of this as if I started with a more microscopic Hamiltonian with a hyperfine interaction, decoupling it in a suitable channel via Hubbard-Stratonovich, and then I guess ignoring a bunch of other stuff?
There's a slight difference, or actually important conceptual difference. Well, obviously if you do everything microscopically, this will come out. But what you need is, what's important about this model, as compared to the usual 4 Fermi model we normally use, and then maybe decouple it in the BCS channel, is that the boson you decouple it with has kinetic energy already, even, it doesn't have to be induced by integrating out fermions. There's a kinetic energy p squared over 4m of these bosons. So this is a true point particle. You might ask, well, why is this a point particle? Well, the size of this bound state is set by the scale of the potential, microscopic scale of potential. So it's really, these guys are 10,000 angstroms apart. And this guy is just, maybe 20 angstrom size. So this guy is truly point particle. And it really has kinetic energy, it has, you really should think of it as a particle. If you, as you will see, when we go to broad resonances, I'm sort of jumping ahead a little bit, but since you asked, for broad resonances, I'm going to ignore this guy, and then it really looks like a Hubbard-Stratonovich field of the 4 Fermi model. But it's not as complete as the 2-channel model. But the 2-channel model reduces to a 1-channel model of, simply Hubbard-Stratonovich transformed 1-channel model when this term is small. Yeah, Andre?
We spent about 15 minutes before talking about solution for scattering, and the imaginary part was important.
Mm-hmm.
Now we see a phi field which is completely real.
Exactly.
Propagator is totally real.
Right, but I haven't used this theory to calculate the scattering amplitude. The whole point is, I'll take this theory and calculate the scattering amplitude, and I will get that structure. You can already see it. So you see it maybe even quicker. Suppose I didn't do anything, I just simply ignored this. So what's the scattering amplitude of of two fermions. Well, the scattering amplitude of two fermions is
Psi and phi are decoupled.
yeah, psi and phi are decoupled. So then, well, let's make this tiny infinitesimal. Okay, I still need to make it infinitesimal. Then two fermions come in, and they can become a molecule, and then it will decay. Okay, so this is up, this is down. And so what is this? This is a phi-phi propagator. This phi-phi propagator, in the limit where I ignore g, I only need g because of these vertices, the scattering amplitude is going to be proportional to g squared, because of these two vertices, times the phi-phi propagator. And that guy is g squared, and the phi-phi propagator is just the inverse of this. Okay, so it's going to be, in real time, it's going to be energy minus p squared over 4m plus epsilon 0 minus epsilon 0 plus I 0 plus. Okay, so as Andre pointed out, there's no imaginary part, but let's compare this guy to this thing, what I claim this guy is. Let's look at L equals 0. So this guy is 1 over minus A inverse S wave plus RS over 2 K squared plus some imaginary part. Minus IK, I'm going to get my signs. I think there's a, I'm going to get my sign.
Overall minus sign.
I think there's an overall minus sign. So I just want to show you schematically. So this K squared RS over 2 is this guy. Up to, you know, if I divide it by G squared, let me divide both sides by G squared. Okay, so 1 over 4m G squared is RS squared. Notice when G goes to 0, RS becomes long, and that's what I need. When the hyperfine direction is weak, when the barrier is large, and the molecule lives a long time, RS is huge. G coupling is small. And but anyway, but you're getting this chop to K squared. You also see that it's negative because of minus P squared over 2M. So it's minus. That's exactly that RS being negative. I think this is actually plus. Okay? So that's what, so this model gives you that.
So we've missed the IK.
Why do you need
I'm missing the IK, exactly.
You replace it by I0.
I replace by 0, but that's just a cheat, you know, I didn't do anything. I really need to calculate true propagator here, but the true propagator, looking ahead, and I'm going to quit at this point, I need to include, you know, because that boson is going to decay into two fermions, and I have to include this whole thing.
So that will
And this guy will give me minus IK. Okay? Okay, so you can think of it as Landau Dampier, or even just in the scattering of even two particles, you're getting this imaginary part. So I think I'm going to quit at this point. I've introduced the model, I've done all the background. I think the rest of it is, although it's the meat of it, will go much faster tomorrow. So I'll pause here and take some questions if there's still more, and then we can go for break for coffee.
Thanks very much. If there are questions.
It looks like you can just integrate out phi here, and there's not going to be any damping that appears in the four fermion interaction.
So you can integrate out, right? But then you have a four Fermi interacting model with a non-local kernel. It's not going to be a point interaction because this guy is momentum dependent, and you do it in the packages, you do it in the Lagrange level. So there's also minus I omega here.
Okay.
So this is going to be, you indeed will get full Fermi interaction, which is proportional to g squared, but its propagator is going to be, its kernel is going to be 1 over omega squared plus b squared. And so you have to deal with that full Fermi model if you want.
Okay.
You can do that, but it's just, you know, it's equivalent if you wish, but it's not as physical. We don't like to integrate things that are potentially going through zero or non-local. It doesn't really add anything to you.
Okay.
More questions? Well, if not, then we have 25 minutes break. Come back at 11.
But actually, before you guys leave, so not non-physical, I want to ask if there's people who have not picked up their t-shirts could stick around and not get coffee yet and just come down, go up to there, and I'm gonna check you off and you pick up your t-shirt. And also, if you have somebody for whom you can pick up a t-shirt, also go over there, please. So then we can get rid of as many t-shirts as possible.
It's not like Delta. Because it's in a particle structure.
Let me just shout. Can you take care of this? So, just try to pull out that box and try to hand out those t-shirts. And encourage people to, there's particularly, you can look at the list and see who is not picked up their t-shirt and just call their name. And then also encourage them to take it for their friends.
So, I was wondering, so in this kind of field, I categorize this as multiple scattering.
That's right.
So it's clearly not.
No, absolutely, you won't get it. That's right, you won't get it.
Right. Thank you.
Say that?
That was just the scattering theory.
Right, but these particles are all, you'll never see particle hole bubble here, you only see particle.
Yeah, I know.
So you do have to read some multiple scattering, just like you do for simple scattering of particle from a potential. But only at any one instant in time, it always only involves two particles. There's never a sea of particles. All these are retarded propagators.
And the reason why
Exactly. I'm just studying. This is just a fake way to study. Like if you wish, a complicated way to study just two particle problems. Which I don't need that machinery. I really much rather just go to relative quantities on such very good questions.
Right.
But I'm doing it in the field theoretic. I'm reformulating the field theoretic way because once I formulate the field theoretic, I can add chemical potential to this. And now I can study fine density. Many bounds. But you're exactly right.
Yeah, but it's still correct to this picture. So over there,
if you wish. Absolutely. But look, that's why it's always particle particles. I never have a hole. I can only have a hole, I have a Fermi seed. Then I can think about particles. So literally, if you go for two particles and compute this diagram, you can't even write down this stuff. Because that's not there. You can write this down. So everything has to be constant. But then you can write this down. But then, if you actually compute it, you get 0. Because this guy is being created before it's destroyed. Right. And so if you really have states that only have two particles, just two particles.
But I always wondered, so I always wondered about preceding piece.
Okay.
Whenever I really had the time to look into it.
So in our long paper,
Right, so I should really.
yeah, it's like a bunch of paper which has everything. Anything can possibly be purely general arguments, detailed calculation. on all different limits. Okay, so what I would do is, kind of, how should I say, pragmatically, I would go experimental to T2 far from the resident. That would define for me a background interaction, non-resident. That would define for me a background interaction. Then I would
一直的考虑到这个还有一个配置框架，然后给这个说明给你的那个AS。但是没考虑来到单品。其实你去看闪光有这一套。
Scanning theory.
The scanning theory 就是闪光。
Yeah. Yeah, for example, then it won't work. You won't be able to.
不是数据里头用常的，然后数据 scanner theory 这一套的话，你就去拿那个，就是 scanner theory 它这个 AS 发散就正好用的。
This actually is really specialized.
方式内。
When I break it up into channels, into
其他它就对应的，所以说它说即使是你这个 track 它是想变大的时候 ，AS 是有广告的，是吧？所以它就说 其实相当于建第一个方式。
Can I ask you to print my air ticket receipt?
Print?
Yeah, print.
Okay, have I given your card?
Yeah.
I think I have given you a card, right? No, it's not this card, the printing card.
No, I don't have any card.
Alright, so you can, I can give you a printing card and remember to give it back to me.
Yeah, I can.
And
so now they work, yeah?
I think you need to go to the library.
Can I ask you just to send it to you and you just print to explore? Can I do this?
Alright, so...
Can you write your email?
No, so...
Yeah.
Much faster.
But I just don't want everybody to have me.
Okay, I will not do
Right, so the problem is that we need to take some limits. For example, suppose our limit is G is very small.
Yeah, and then I use U and U1.
Then we can use states that are labeled by electron spin times mu C and U. Then it's very simple. Then we can take it, you can classify
Because we don't talk about it.
singlet and triplet electrons.
Yes, and also one and one, you know, one portal with one whole pocket, one electron pocket can be emitted.
So then the
Right,
closed
you need
chain.
two electron pockets for electricity, otherwise it breaks C4.
So two atoms can be with this electric spin.
Okay, let me grab coffee and then I'll come back.
Sure. In the open channel where they live in the cloud, they're like this. They're electronic spins.